Yes, from UCL.
Thank you. So I would like to first thank the organizers of the whole semester for such a wonderful set of workshops, and I hope that by speaking last in the last workshop I won't ruin it. It's an Herculean effort that you have put together this set of workshops, and even the organizers of each workshop have worked tremendously hard. I mean, I know how I suffered in the workshop too. So I'd like to talk about some work on inversion, because this is the topic of this workshop. And what we've been working with was a climate model. So Kai Lan Sheng has done all the work, basically. He's my PhD student, former PhD student, now he's NLC fellow in Boulder, Colorado. And we were looking at climate models, and Danny and others have been examining these models, and these models have outputs that are large. They are on the sphere typically. The resolution is large, and they have many parameters. And I will justify the use of parameterizations in a second. However, these parameters are unknown. Many of these parameters are unknown. They cannot be even measured. They have fudge factors. One needs to tune these parameters in order to make climate predictions that are more accurate for the future. It seems doable, but it's not. In terms of targeting some parameterizations, I'll show some results here, but I don't believe that it's clearly feasible now. I mean, we are aiming at doing it, that's it. It's just work in progress in some way. So what we'll talk about is a spherical representation of these outputs, so these spherical harmonics that have been obviously used before in other contexts. We'll look at some synthetic examples, some comparison with principal components, for example, that Dave Higdon proposed a decade ago. And we look now at the third point is maybe more innovative, the fact that we could use some, let's say, derivative information or non-stationarity information in the outputs of these computer models. So representing the outputs of the computer model using Gaussian fields, obviously, but making use of the scale and the precision parameters that can vary across space, the new idea of INLA-SPDE. And we'll apply this to Wacom. So the Bayesian calibration framework, or Bayesian inversion framework for computer models is as follows. We here in this work we assume that the computer model is deterministic. We want to infer the values of the parameters that match the observations. So we learn from the observations in order to infer these parameters. We can have irregularly spaced observations. There's a nice framework by Kennedy and O'Hagan from 2001 that I will follow, looking at observation errors and model inadequacy. So that's the attempt to motivate the computer model that we're targeting. So this is, let me not launch the movie yet, if it works. So this is at a particular latitude, and we're looking at longitude here, and we're looking at winds, what's called zonal wind, so in a certain direction, across altitude. And altitude in those models is either in kilometers or in pressure. Geophysicists prefer pressure in many ways. And this is actually an extension of the climate model I'm running. So the climate model from NCAR, the US model, CESM, the community model, typically goes to a certain height. Then I use a version that extends this height up to the mesosphere, and this is an extension of this extension by Henley Liu. So if you look at the wind now, you can see in the troposphere the wind is not varying much, but then in the stratosphere and upward, the winds are stronger. And the gravity waves are the phenomenon that's driving this process. These waves are generated in these regions, propagate upwards, and break in the upper atmosphere. This is parameterized, and this is maybe the number 2 problem in climate science after cloud physics. The parameterizations in cloud physics are really a big issue, and this is maybe number 2 there. there are certain difficulties in climate modeling, such as sudden stratospheric warmings in the poles. The quasi-biennial oscillation also that needs to be modeled right. This is an oscillation of these patterns over 28 months roughly. So these are very important processes that are not well modeled currently. So a recent paper by Rolando Garcia looked at the improvement of these parametrizations for the flows generated over orography. So you have winds on the troposphere, and then you have a mountain, and the wind hits the mountain and then generates these gravity waves that are going upwards. The first talk of this workshop was about gravitational waves, which are also linked to gravity, obviously, but in the framework of relativity, and this is more a Newtonian approach. Obviously, we're looking at gravity waves on Earth, and the point 2 and 3 is the ones that we are looking at here. When you have either fronts or convections, that you generate these waves and they propagate upwards and they break and they have an influence on stratospheric chemistry, ozone, etc. Many things are very important. So there's an explicit scheme actually. Some NCAR is running at very high resolution some new schemes now. But for climate modeling, when you have to look at decades of runs, then you have to use lower resolution for practical purposes. So you have to have a parametrization, unfortunately, somewhere. So the Kennedy-O'Hagan framework for Bayesian inversion, it's not new, obviously. It's been heavily used and successfully in many ways, and there are some difficulties though. But so what's that? So you have the reality, which is observed through field data and with error, and reality should match the computer model outputs at some location S in space, and theta star is the optimal choice of parameters that you can use in order to match reality. And there's a discrepancy, unfortunately, delta, which is representing the unknown physics or the lack of resolution in the model. And this is very helpful and necessary. Whoops, that's not me again. I just wait for it to come back. Yeah. So this is the framework of Kennedy. Now
it's getting personal.
Yes. Yeah. So obviously two categories. No, it's not. So I can continue. Yeah. I can move on to maybe the next slide if it's this projector is allergic to this formulation, maybe. So obviously we assume that I'll go quickly this way. This error here, we assume normal typically. We parameterize this typically with the precision. There's a bias, the discrepancy, again, inadequacy of the modeling. There's a big issue here. If you write this in one line, obviously you can write field data equals eta plus delta plus epsilon. There's a lot of confounding issues here between these two. But you want that delta because you can overtune these parameters. You can change the gravity constants, say, for example, in the model, and match better the observations. Really? Okay, things like that, you know. So, and what are the true values of these parameters? Sometimes they don't have a physical meaning, really. So to alleviate this problem, we often put strong priors on these on the parameters driving these processes. Anyway, so we usually assume that we have a Gaussian process associated with the computer model, and the same for the discrepancies, where you have a sum of two Gaussian processes in that framework, and this is a way of parametrizing the typical square exponential, but we can vary those. We can be more general than that, but this is helpful. So this is standard stuff, and the inference is a fully Bayesian inference, typically, where you look at the likelihood here and parameterize in this way the problem, and you make inference about these parameters, these hyperparameters, and the parameters of interest that are the calibration parameters theta. You typically make some assumptions of this kind, and I use. I'm not doing something very original here. Okay, so this is nice when you have outputs of a computer model that are just numbers, let's say. But when you have large outputs in terms of dimension, for example, a spatial output, like a climate output on a grid, this is problematic. So people have thought about this before. I mean, Suzy Bayari, obviously, wavelets for time series, and that was a very smart move, and Dave Higdon for using principal components. In terms of spatial modeling, how do you model processes on the sphere? There's nice work by Michael Stein and Mi-Kyung Jun in the last decade as well, looking at spherical harmonics, and we're going to follow that route. However, we are going to use a different framework for spatial statistics, because nowadays we have these nice INLA-SPDE framework. I want to say that Wang Chang and Murali Aran and collaborators have published a nice paper in 2015 where they try to reduce the dimensionality of the problem by looking at composite likelihood. That means breaking the problem into blocks. Spatially, you take blocks and then you put it together, you recompose it using this approach. So you gain a lot computationally, but you also lose something, obviously. For example, it's only the stationary case. We will address the non-stationary case, and maybe at some point, our technique, I have not given you any insight into these numbers, but we can go faster also in some instances. So we use the spherical harmonics representation. So the spherical harmonics are, let's say, the equivalent of the Fourier modes on the sphere. So you can make you can represent any function roughly with this expansion. So these functions on the sphere, I can show you immediately what they are. These are the functions that are explicitly written here. So the Legendre polynomials are employed here, sine, cosine, in latitude, longitude. They seem unfriendly, but they are going to be helpful in expanding those functions on the sphere. And then we're going to follow that route. We're going to decompose the field observations, the model outputs in those spaces. So that's what we're doing. So the model output, again, eta, is decomposed into that basis. There's some approximation error here that we are neglecting. But you have a coefficient. You have coefficients associated with this expansion. So we immediately reduce the dimensionality of the problem by targeting the coefficients. That's what we're going to do. And eta is the number of basis functions used. It's not that large. You'll see that later. Same for the field observation, ny. But there's a tension here. So how do we choose ny and eta? Obviously, field observations encapsulate a lot more physics than a computer model. So you should have ny greater than eta, and that's what we're doing. Same thing for the reality, but reality is just a step in the thinking. So it's, but the discrepancy is also expanded along those lines. The noise as well in some way. And so again, eta is smaller than ny. And then we choose 0 for the set of coefficients of the computer model along the index, or for the indices that are greater than n eta. So in the end, we recast the problem that we had initially on outputs onto coefficients. So we're matching coefficients. Again, it's not completely novel, but it's this approach of field data is a computer model with discrepancy plus noise, observational noise. So we have to make some choices, and I'll show some examples of that. We have this setting that's okay. That works quite well so far. Let's see on examples. We assume again Gaussian process assumptions on the coefficient directly, and we assume some independence across coefficients, which is a strong assumption. Why should they be independent across scales in some way? But it works. But maybe it's not that strong. Think about it. And the same framework, exactly the same framework, but it's on the coefficient. So I may skip that. We carry out the inference again. Typically, we can do better than this, but this is just to explore and make the inference of theta. So we want to tune the model and match the observations best. Priors, there are many choices to be made, and Again, I'm using very standard approaches in terms of choices of priors. We want to give preference to the computer model. We don't want to explain everything by the discrepancy, obviously, so you give priors that are explicitly encapsulating that information unless the data sway your opinion. This is a Bayesian approach. The dimension of the expansion, so this is order of the expansion. There are two types of expansion that I will discuss. A full expansion, a restricted expansion, using the trick here that you have some symmetry in the expansion, so you can reduce the dimension of the problem. It's not very important here, but it's a trick to reduce the calculations. And here is an example. So an example here of a function that's a computer model, a synthetic computer model that we know very well. You see a function of these spherical coordinates, a polynomial. Here is very simple. Theta 1, theta 2, theta 3 are selected at those values, and we want to test our method. So obviously here we simulate outputs on a grid that matches the same grid as the computer model, the climate model that we're targeting, just to get a feeling of the quality of this method. 13,000 locations, roughly. And then we add a bias and some noise. And then we make inference with some, 25, 50 simulations for 3 parameters, sorry. And then it works. Okay, it's wrong to show tables in a presentation, but computational time increases. This is the restricted expansion. It works as well. It works as almost better, but you have to use an expansion that's not so small and to get results that are kind of correct. But if you go too far, then you spend a lot of time, and you'll see later that you also lose in terms of uncertainty, etc. So these are the fit across design. So we replicated the design 100 times, and it turns out that we get the same result. So we are satisfied with that. Now, using different expansion numbers for the computer model, expansion order, sorry, computer model and the field observations. So you see different orders, always smaller. You get different results, and you have sweet spots. I mean, we don't have a theory for that, obviously. It depends on, it's problem driven. But you don't want to go too far. You'll see later a bit more about this. Okay. And these are the discrepancies. So this discrepancy is the one that's assumed by this model, and how we do not really capture this discrepancy in model A, for example. You see the numbers are not exactly matching the parameters of interest, but in model C and B we do better. Another example with comparison with principal components. So this expansion of spherical harmonics, we could have done it on principal component, looking at the variability of the field using a principal component analysis, or it's called EOF in geophysics, and that's what Hingdon and colleagues have done, and successfully. But here we're going to show an example where it doesn't work. As you see, it's so theta 1, theta 2, theta 3 are parameters of interest, again, but the function is slightly more complicated than earlier. Again, some little discrepancy and noise that I won't discuss. If you look at the field surface, some example of one field surface generated by this. So PCs are computed here, and you see capture about 92% of the variability of the field using 3. And Dave Higdon has published this paper in JASA in 2008, where they reduced the dimensionality of the field to a lower number, and then they do the same calibration exercise. Oops. And if you do this, these parameters are the true values. We know them because it's synthetic. If these actually don't converge. I will show you that in the next slide. Maybe this is better. So this is principal component using 9 EOF. It doesn't converge. You can see this part of the Markov chains don't converge. So it's slightly akin to the terminal case that Danny Williamson coined in terms of, well, we are not getting, we're not understanding the relationship between the model outputs and the observations. Maybe we have a basis that's not good enough for this comparison. Using second order spherical harmonics representation, 9 coefficients to be matching the complexity, we immediately converge, or almost immediately burning and converge to the right numbers. Now the next step is to include derivative information. So let's say non-stationary information about the way the correlation varies across space. So and in climate modeling, it is the case that correlations across space is here, if we look at winds, are different in the poles or in the tropics, for example. So you want to encapsulate that in modeling. Obviously, if you do that in a traditional way, in spatial statistics, it's quite difficult. I mean, Michael Stein and Mi-Kyung Jun have looked at this. It's difficult. But now we have a tool which is the SPDE framework by Phil Lindgren from Edinburgh. Now at Edinburgh. So this is really, really helpful. It's again fully Bayesian, and it's going to include automatically this information through a Matern field. So let me in one slide roughly explain to you what's happening. So you have on the field. So you have here the Gaussian field whose covariance is Matern. There's a one-to-one correspondence between the field here, driven by this covariance function, or with underlying covariance function Matern, with these parameters, K, kappa, nu, and tau, and the solution of a stochastic partial differential equation. This is Whittle's work. I think Andrew mentioned that in a different context. The solution of the SPDE X is also the field, the Gaussian field whose covariance is Matern with these parameters. And there's a relationship here between nu, d, the dimension 2 here for us, but it could be used in 3 or more dimensions. Nu and alpha. So in the package in INLA-SPDE, actually alpha is only equal to 2. I think now they are working on different numbers, but if you have equal to 2, then it imposes the smoothness of the field, because d is fixed to 2 at 1. So this is really nice, except that why is it so nice? Because it looks like solving a stochastic PDE is not making much progress. It's complex to solve a stochastic PDE. This is precision and scale. Scale you understand from this expression that you have the length of the vector here, and at which length does it decay in some way, and precision because 1 over tau times the white note. Yeah. Oops. Now the extension that Lindgren and collaborators have done is to a non-stationary spatial fields, and that's a leap. I think that's a leap, because in traditional spatial statistics, there were many attempts in the last decades at this non-stationary representation of spatial fields, but very, very difficult to do. And this is working very well, except that you have to parameterize this kappa and tau across space, and it turns out that you can do it using spherical harmonics. So we use the same basis as earlier. And how do you solve this stochastic PDE? By using a finite element representation. With another PhD student of mine and a collaborator from the US, we also extended that to variate splines. It can be useful in some context. But anyways, this is really helpful because if you have a representation of the non-stationarity across space through kappa and tau, you can solve this stochastic PDE efficiently. Also, these are very efficient methods making use of sparsity and the INLA approximation that Claudia talked about. So this is really a leap in my view. So if you do that, if you represent the spherical outputs using these representations of variate splines and these kappa and s in the same way, then you suddenly build a let's say a vector of 3 components of coefficients. So you start with field observations, you transform them into C, the coefficients in the spherical harmonic spaces, and then the kappa and tau in the same basis. And the same thing for the computer model at each of these iterations of the parameters, and when you build your data matrix. So you have ny, n kappa and tau, because you also expand those. So you have triplets, you have coefficients for each of these characteristics of the field and of the derivative information if you want, or the non-stationarity information. I'll skip all this because I think time is flying. These are comments that I can make later. We try that in, we created another non-stationary field that, if this is a latitude, I think. Yeah, it depends on latitude. So you can have a different type of correlation or different type of function, and therefore of correlation. If the latitude is different, we add some noise, we know the truth. And again, this is choosing the expansion order here for eta, for kappa, for tau in this spherical harmonics basis. And I want to emphasize that I wanted to put it in red. I didn't succeed in the morning in the train, but here I want to emphasize this. This is using only derivative information. And actually my PhD student Kailan was doing this only until I noticed this mistake. And actually it's a great mistake. It's a bit like the tarte tatin, if you know the mistake of these sisters that cooked the apple pie upside down in the oven and created the tarte tatin, which is a famous. Okay, I hope that this will be as successful as the tarte tatin. But anyway, so well, using not even comparing observations with model outputs, only using, let's say, secondary information about these. Kailan was able to calibrate, almost, quite well this thing, whatever. This is the analysis of that. I have what, 5 minutes, 2 minutes? 5, okay. So if we jump to the problem of climate modeling now, real and not these synthetic functions that you play with. So it's called WACAM, the Whole Atmosphere Community Climate Model, an extension of CESM. It goes up to 145 kilometers, 66 levels versus a regular climate model that you run as maybe 20-something levels. At this resolution, we played a lot with this. It took time to run it on our supercomputer Legion. And we cannot run it for more than a few months, and we should run it for multiples of 28 months in order to capture this quasi-binaural oscillation that we want to tune. So this is really an attempt to do something quickly. Anyway, so it takes time to do this because this is 1.2 million lines of code. This is probably one of the largest models on Earth. We have to change those parameters in the code, so we have to change a Fortran subset, subprogram, and then recompile. It takes about 40 minutes with Intel compilers to whatever. So it's just a lot of work. Anyways, these are the parameters of interest, the 4 parameters of interest that control the gravity wave modeling in this model. And there are lots of questions about this, and they are chosen to be some number right now, and they are not satisfactory. The launch levels, the momentum flux, this is deep science in some way. And we're comparing with some observations. First we'll do synthetic, but then real observations. So we validate first on synthetic observations where we use the standard values as the truth, and we modify that with some discrepancy, some noise. And then we'll use ECMWF data, ERA 40 to do this. So it's synthetic. So we're going to try to to see if our method works. If Mother Nature is a computer model, which is WACAM with the standard standard input parameters or the standard parameterization, and we add some noise and some discrepancy that you see depends on these spherical representation of the field. So well, we take some noise that's not too large, obviously, but it's this is a formulation that can be displayed here. So standard outputs, that means the computer model with the default values, and you see some discrepancy here and there. We introduce some differences to make it a bit harder, obviously. Okay, so if you do that, and we compare 4 models, so A is the ultimate one, the non-stationary model with spherical harmonics with SPDE parameters, kappa and tau included, a stationary version which has no varying kappa and tau, and then 5 principal components, 10 principal components. By the way, C and D again do not converge, so the method doesn't work with principal components, but for those 2 they converge. But for the stationary case, to the wrong value, so this is 0. It's actually at the boundary of the prime is at the boundary of the interval of interest. We don't. These are rescaled to 0, 1, by the way. We never get this. But with this non-stationary method, we find it. This is the true value because again we run the default scheme. This is fine. Again, this is fine. And okay, but these are actually not significant. I mean, they're not even convergent. So this method looks promising. And this is the posterior. If you look on the right, these are the true values, and these are the histograms using the MCMC draws. Again, you see this value of 0, which is the true value, is only on the left side, but it looks like it's working, right? Now, if we do it against real observations, then we don't know the true parameters. We are actually trying to find those values, comparing with observations. But you know, again, this is what is observations. It's just a month here that we're looking at. But anyway, so these are observations at 1 millibar, which is quite high. I can show you probably some of these. Yes, these are the observations made at 1 millibar in altitude, and this is the standard output from Wacom using the standard parameterization. So you see some discrepancy, obviously, for that particular month of February 2000. You know, you can tell that some patterns are similar, but you know, there's some issue here, right? Danny in his talk in the second workshop, I think he showed many of these discrepancies for many types of fields. These are the same thing, but across latitude, averaging over longitude. This is not so important, it's just how much it varies. And then we carry out the Bayesian inversion, and we get those parameters. So we run multiple chains as well, and somehow these are converging to values that seemingly are satisfactory. Again, it's a statement that's fuzzy, but it's, you know, you will validate that in a second. But you know, okay, so we get some differences, some discrepancies. Maybe we can learn about the physical deficiencies, the deficiencies in the models, looking at discrepancies, and actually looking at RMSE. So comparing. So if you run the model forward, so we did the calibration using values in 2000, and then we run the model forward using the standard parameterizations or the standard parameterization or the calibrated parameterization. And if you look at the global impact, not so much, but in the tropics, we really improve the phenomenon. And it should be the case, because mostly, since we're using observations at that level for that particular time, we should improve in the tropics, and it is the case. Not always, but we reduce by about 20%, maybe, about 20% overall in the tropics. And that's the last statement, maybe, that we have some kind of whack-a-mole behavior, as they call it. These people looking at parameterizations in Wacom, they call it whack-a-mole, because you know, you find a mole and you tune a parameterization, and it creates another problem with another set of parameters that we have not discussed in another scheme, and then you hit that one, and then it pops up elsewhere like moles, you know, in your garden. So so they call it whack-a-mole. That's a very big problem. So I'm not claiming here that I'm solving you know, concretely that I'm solving this problem of gravity wave parameterization, but I'm trying to understand what's going on. We need longer runs, and you know, we need to work a lot more and with lots more computing. But at least I hope that we made a point that we can improve some parameterizations in highly complex models using this technique for spherical outputs. Thank you.
Yes. Small question. Do you know what is better, to use Euclidean distance or geodesic distance? Is it crucial or not?
There are papers about that, actually. What is the best distance to use? Chordal distance is one of the best.
Euclidean distance?
Yeah. No.
Geodesic.
It is even, yeah, okay. We can talk offline. With the validity of covariance models on the sphere requires the use of a certain distance.
Any other questions? Okay, I have one then. Your discrepancy you put on the same spherical harmonic basis, truncated in the same way. And I wondered whether actually you might expect some of the discrepancy to be either in some of the things that you've truncated, or in like maybe some areas the models care about that the modelers care about that isn't represented neatly by that construction.
So the discrepancy is expanded in a larger set of functions, the ny. So it's expanded obviously in the set of functions that are associated with observations, ny. And the model outputs are only expanded in a smaller set of functions. So the discrepancy automatically picks up those differences and may help the modelers understand the nature of these discrepancies. Maybe you have had this interaction with modelers. If you tune the parameterization and if you find some discrepancy that means something to the modelers, and they can say, "Oh, we didn't pick up that particular phenomenon." I think it's progress. We're not there yet. It's a difficult discussion.
Oh, Peter, yeah.
I'm going to follow on to that, because some of these discrepancies are going to be very local, and your spherical harmonics are very global.
Yeah.
And somebody using something like spherical wavelets that might allow you to get down to these more local phenomena that are related to the topography underlying or something.
Yes. No, you're right. We can use maybe dictionaries of expansions. Yes, you're right. Wavelets have been used, by the way, for time series to pick up these sudden variations. Yes. That's. There are also splines on the sphere. Spherical harmonics are more global. Though if you use an expansion that's going further and further, then you can go more local and local. But you pay a price for that because you have an explosion of the number. So you may be right.
But if you move one here, you tend to move the whole.
Yeah.
So it's like a Fourier.
It's more like a Fourier expansion.
Local phenomena.
Local is best if you have a. Actually, there are many things that are local. At the poles, they expect some in the southern pole especially, they expect some deficiency that's due to the polar vortex and whatever. This issue.
You're thinking the tropics might be different in the Pacific than the Atlantic.
Yes, also yes, because orography. So this is one of the. I haven't tackled that, but the fact that the Earth is not just a sphere. Obviously, there are mountain ranges, and that's one of the deficiencies also in the model that these waves are generated through. Yes.
Is there an analog of spherical, so harmonic wavelets on the sphere? I mean, by harmonic wavelet, I typically mean sin x ln x, sinc functions. Are there things like that which would meet Peter's point?
I don't know about this.
I believe so.
You believe so. If you believe it, I believe it.
Yes, I believe it.
Okay, let's continue the discussion over coffee, and thanks, Charles.